Okay, let's now define a Taylor polynomial. So let f be a function where f prime, f double prime, out to fn, the nth derivative, are all defined at some point a. The nth order, or commonly referred to as the nth degree, Taylor polynomial for f centered at a, which is typically denoted by p sub n, the nth polynomial, has the following properties. Pn of a equals f of a, so we're saying we're going to match points. And all derivatives up to and including the nth derivative all match. So if I take Pn, the nth derivative, and I take the derivative of this, Pn, the nth polynomial, and I take the nth derivative, I will end up with the nth derivative of a. That's what I kind of showed in that last little example. I did it for the first degree polynomial, the second, and then the third. So this extends out to the nth. Now, we can write this whole thing much more compactly as a power series. And I'm going to write this as the sum. Oops, that was pretty ugly. Let's do that again. K equals 0 to n. This is not an infinite series. Of ck, which is some constant, times x minus a raised to the k. So this is a power series. Now, what's special here is ck. Because ck is really nothing more than the kth derivative of a, or of the function evaluated at a, divided by k factorial. And that's exactly what we have going on here. See, here's the second derivative. If I move this 2 factorial right here, if I move this n factorial to right here, these are my ck's, my constant terms that's out front of this term right here. So, understanding this basic idea, I can immediately come up with nth degree polynomials to approximate transcendental functions. So, let's go ahead and find the 6th degree Taylor polynomial for f of x equals sine of x near pi equals, or near x equals pi over 6. This is my value of a. Now, we've already actually done this for the 3rd degree, but let's just quickly walk through the whole process here. So the first thing I'm going to do, I'm going to say, all right, a is equal to pi over 6. So I need to match a point. Sine of pi over 6 equals a half. So I know my point is going to be 1/2. Whoops, I did that backwards. My point is going to be pi over 6, 1/2. So let's just start looking for derivatives here. See, f of x equals sine of x. So I want f prime of x. Actually, I don't want f prime of x. I'm going to do this much quicker. I want f prime of pi over 6. Well, the first derivative of sine is cosine, so I want cosine of pi over 6, which equals root 3 over 2. Now I want f double prime of pi over 6. That's the derivative of cosine, which is negative sine of pi over 6, which equals negative 1/2. So now I want f triple prime of pi over 6, the 3rd degree, or 3rd derivative, which is negative cosine pi over 6, which is negative root 3 over 2. I'm going to move over here because I want to write the rest of this down here in the bottom. So see, I want the 4th derivative at pi over 6. Well, the derivative of negative cosine is sine. So this would be sine of pi over 6, which is 1/2. The fifth derivative at pi over 6 is cosine pi over 6, which is root 3 over 2. And then finally, the sixth derivative at pi over 6 is negative sine pi over 6, which is negative 1/2. And you can see it's cyclic. If I keep going, I'm going to have the same pattern. I'm going to have, you know what, I'm going to add one thing to this just quickly, just to make a point. I didn't do the 0th derivative. Well, I did, I just didn't call it the 0th derivative. So the 0th derivative at pi over 6 is sine of pi over 6, which equals 1/2. That's actually my point. So I have the 0th, the 1st, the 2nd, the 3rd, the 4th, the 5th, the 6th. And the reason I did that is because of this power series. It goes from 0, so I have the 0th derivative. Right here would be the 0th derivative. So it actually matches what I said it would in terms of that power series. So now all I need to do is put this all together. And I'm going to say that P6, my 6th degree polynomial approximation for sine of x near x equals pi over 6, or a equals pi over 6, is going to be my point, 1/2. Now notice that this is actually 1/2 times x minus pi over 6 to the 0 over 0 factorial. I would never write it this way except for to show you what I'm doing, because this is just 1, this is just 1, so the whole thing is just 1/2. So all of this can go away. There's no reason to put it there, but I wanted to point that out because it does follow this format. It does follow what the power series said it would do. So then I'm going to add to it the first derivative, which is root 3 over 2 times x minus pi over 6 to the first over 1 factorial. See, I would never do the ones, but I'm just doing it again so you can see it actually does follow that pattern. And then minus 1/2 x minus pi over 6 squared over 2 factorial. F triple prime was minus root 3 over 2, so that's times x minus pi over 6 cubed over 3 factorial. Then I need the fourth derivative, which is going to be plus 1/2 x minus pi over 6 to the 4th over 4 factorial. Then have the fifth, which is plus root 3 over 2 x minus pi over 6 to the 5th over 5 factorial. And then finally the sixth, which is a negative 1/2 x minus pi over 6 to the 6th over 6 factorial. So now I have this polynomial that's going to do a really nice job of approximating sine of x near pi over 6. And actually, the more and more terms that I add, the farther and farther away from pi over 6 I can get. Okay, so I went ahead and enter in the 6th degree polynomial, and let's take a look at it. And something's not right. Let's take a look here again. Oh, all I did was a polynomial, and I kind of forgot to put in sine of x so we could compare it. Okay, so I put sine of x back in there, and here we go. You can see this is sine x, and you can see all the way out to here, looking at the graph, you can hardly even tell the difference between sine of x and our 6th degree polynomial. And of course, the 1st degree polynomial is still in there. I can go ahead and get rid of that to help clean it up just a little bit. There, that's better. Now the green one is sine x, and this red one is our 6th degree polynomial. And right in here is pi over 6. and for quite some distance, you really can't tell the difference. So just imagine what would happen if we went out to the 12th or 15th or 100th degree polynomial.